Hello everybody. In the previous lecture, I made an introduction to the concept of pulse transfer function. Okay, and today we will go dig deeper in the concept of pulse transfer function and analyze more complex systems. Okay, the basic idea in the pulse transfer function is given a digital control system where we have continuous time signals, continuous time transfer functions, some sort of sampling, and some sort of zero holds. And the idea is trying to obtain a discrete time transfer function between the sampled input and sampled output. Okay, so this is the basic idea. And pulse transfer function is nothing but a discretization of digital control system. Okay, we try to transform everything into discrete time domain. Okay, and when doing that, we heavily use the concept of start signal, which is a like abstraction of the sampling, and start Laplace transform. Okay, so if we look at the block diagram structure, y of t is the output of g of s, okay, and input of g of s is x star of t, which is the sampled x of t. So in the time domain, we can easily write that y of t is equal to g of t, where g of t is the impulse response of this g of s, which can include continuous time transfer function, and we know that it can also include the zero order Hall transfer function star, which is convolution x star of t. Okay, the basic idea here is g of t is a transfer function and x star of t is the sampled or impulse train based sampled signal of x of t. Okay, so in this case, we know that if we sample y k of t and obtain a discrete time sequence y of k, we can also write y of k in terms of convolution of x of k and g of k, where x of k is simply the sample signal, and where g of k is equal to g of kt is the sampled impulse response of g of s. So somehow, if there is a sampling at input is involved in this digital control system, this whole operation is somewhat fictitiously samples the impulse response of the transfer function to obtain discrete time impulse response, which is quite remarkable from my point of view, and it's not very obvious. Okay, so this is the basic idea in time domain. In S domain or Z domain, okay, so let's go back here. In Laplace domain, we can write that y of s is equal to g of s times x star of s. Okay, so y of s is simply the Laplace transform of the continuous time output. X star of s is the Laplace transform of the continuous looking impulse trained input. Okay, so we know that this is a discrete signal, but we can treat it as a continuous time signal and take the Laplace transform. And g of s is continuous time transfer function of the whole control system here. Okay, or whole plants combined with zero order Holt or other kind of components. Okay, so if we sample y of t, okay, if we obtain y star of t, we can take its Laplace transform, which look like y star of s, which can write it as like this: g of s times x star of s star. Okay, and later we learned that somehow y of y star of s is also equal to g star of s x star of s, or we can transfer everything in the z domain because everything is star. Y of z is equal to g of z x of z. So what does it mean? It means that inside a multiplication, okay, so this is g and this is x, okay, one of them has a star, one of them doesn't have a star, okay, and you put a star at the outside. So what we do is we sample the combination of g of s and x star of s, and we indirectly show that if this involves an x star of s, we can simply add star of g to obtain g star of s x star of s, and we know that star Laplace transform is kind of equal to the z domain transfer function, and we obtain that y of z is equal to g of z and x of z. Okay, so this is the whole basic idea, and we know how we can transform from s to z in terms of s because, for example, g of z is simply equal to g star of s, where s is equal to, or yes, s is equal to 1 over t ln s, or something like that. Okay, so it's not big deal. It's very good. Okay, nice. And now we will solve some examples. Okay, good. Okay, so this is our next example. Okay, so now we will do something else. So we have a continuous time input x of t, and we have a continuous time output y of t. Okay, and we have a continuous time transfer function g of s. Okay, so what happens if I sample x and y separately, somehow independent from the system? Okay, so it's completely different from what we do here. I sample x and supply to my system, and now I don't sample x and supply to the system. I sample x separately. So can we write a transfer function like this? Let's say p of s, p star of s, I don't know, x star of s, or something else. Or can we write y of z is equal to p of z times x of z? Okay, so that's the question. What happens if I sample my input and output system separately and treat the system as a discrete time system? Okay, so we will try to do that. So y of s, okay, y of s is equal to g of s, x of s. Okay, this is nice. So I want to obtain y star of s, which is equal to g of s, x of s star. Okay, but as you can see, there is no star here, no star here. Okay. Unfortunately, in general, almost surely, y star of s is not equal to g star of s, x star of s, or y of z. Let's clean that. Okay. Y of z is not equal to g of z, y of z. Okay, so unfortunately, we can write that. Instead, what we write that is y of s equal to gx star of s, which is nothing but just shorthand notation of g of s, x of s times star. So in this case, what you should do is simply find whole expression for g, find x completely, multiply it. You will have transfer function, let's say p of s. Then you can now compute p star of s, and you can compute p of z. Okay, and the basic idea is, since you cannot separate g and x each other, we cannot find a transfer function between input and output in z domain. It doesn't have like this, which means that we don't have a linear time invariant relation between x of z, or x star of t, and y star of t. So of course there's a relation, they depend on each other, but it's not a linear time invariant dynamical system, because we kind of lose information here, because we sample it separate from what's happening to the system, and of course the input that acts in the two sampling instant can affect the system, and we cannot capture the whole behavior. Okay, so it means that when you're building a digital control system, you should be careful where you're putting your sampling. Okay, very good. So we have a nice example here. Okay, so the first one is the typical one. It's my original pulse force transfer block diagram. We have input x star of t. We have a transfer function which says that 1 over s plus ln 2. We have an output y1 of t, and then we sample y1 to obtain y1 star of t. In the second case, we don't sample x, we directly supply it to the system. Okay, now it's the same system. We have y2 and we sample y2 again. So the question is, can we write y1 star of t is equal to y2 star of t, or y1k is equal to y2k? Okay, so from the first perspective of the previous slide, of course we cannot do that, but it's always nice to do it just direct and see that it doesn't hold in general. And for this problem, it's given that sampling time is equal to 1 second. Okay, very good. So let's start with the first one. Okay, so we know that y1z can be written as g of z, x of z. Why? Because y1 star of s is equal to, let's say, g of s x star of s star, and this is equal to g star of s and x star of s. Okay, so we already showed that, proved that. Okay, no problem. So what is y1z? Y1z is equal to, let's look at x of z. So it's given that x of t is unit step function, u of t. Okay, so if we sample it, x of k will be equal to u of k, and x of z is simply equal to z over z minus 1. Okay, that's good. That's great. So, and what we need is, we need g of z, okay? So g of s is equal to 1 over s plus ln 2, okay? That's good. So what we need to do is, we need to compute g of t, okay, impulse response of the system. Then we need to sample g of k, and we can then find g of z. So in the Laplace tables, in the textbook and the one that I put my website, it gives shortcuts of how you can transform directly from S domain expression to Z domain expression. And we can easily see that this is equal to, so this is Z over Z minus 1. This is equal to Z over Z minus 0.5. Okay, so that's good. So we already computed y1 of z, and let's make partial fraction expansion. y1 of z is equal to 2 of z, 2z divided by z minus 1 minus z over z minus 0.5. We can simply take the inverse Laplace transform, which will be, I guess, equal to y1 of k is equal to, I guess, 2 minus 0.5 to the power k. Okay, so that's it. It's the first one. Now let's look at the second one. Okay, so in this case, unfortunately, we cannot write this is not equal to x of z times g of z. y2 of z is equal to simply gx z. Okay, so it means that y2 of z is equal to z transform of g of s x of s. Okay, so if you remember from my previous video lecture, okay, so of course we cannot take the z transform of a Laplace transform expression, but it means that multiply g and x. Okay, you have a Laplace transform expression. Take the inverse Laplace, you will obtain a time domain expression, which is the technically impulse response of this expression, or like it will be like a time domain expression. Sample time domain expression, take the z transform, you will take the technically z transformation. It is equal to z transform of, okay, what is g of s and x of s? Okay, it is equal to 1 over s plus ln 2, because x of t is unit step function, and we know that it's simple 1 over s. Okay, we have this structure. What I need to do is, I need to take the partial fraction expansion in s domain. Okay, z transform is equal to 1 over ln 2 divided by s minus 1 over ln 2 divided by s plus ln 2. Okay, so I have Laplace transform equation. If we look at the tables, we can see that this is equal to 1 over ln 2 times z over z minus 1 minus z over z minus 0.5. Okay, so if we take the time domain expression, it will be something like that, right? y2 of k is equal to 1 over ln 2, 1 minus 0.5 to the power k. Okay, as you can see, both z domain and y domain expressions between y1 and y2 is completely different. Okay, so they share the same exponentials, same roots, but they have different numerator dynamics or different kind of coefficient dynamics. Okay, so by sampling input and output, okay, or not sampling input and output, you cannot change the poles or exponentials, but you can change the behavior of the system. And it simply shows that you should be careful when you are discretizing a transfer function or Laplace domain expression. Okay, if you multiply two Laplace expressions, such as like g of s, x star of s, if one of them is a star, there's no problem. You can start individual. It means that you can discretize G separately. Okay. But if there's no star in between, and if you want to star it, which means that discretize it, you should combine them first, then take the star operation to make the discretization and move on with that. Okay, so this is the basic idea, and I really recommend you to go over with the example by yourself to better understand the concept and details, and read the book in the associated topics. Okay, good. So let's make some examples to better understand the path transfer function concept. Okay, so we have a cascade structure, but it's a digital control system. Okay, so x of t is sampled here. We have a g of s, u of t. It's a continuous time signal. We sample u of t, obtain u star of t. H of s is a continuous transfer function. It provides y of t, and then we finally sample y of t, we obtain y star of t. And the basic idea: can we find a path transfer function of the system? And if we can, what is the structure? Okay, so let's start with this. U of s is equal to technically g of s times x star of s. Okay, so we sample u here. Let's do it. U star of s is equal to, okay, so, and I will change the color. Okay, g of s x star of s star. Okay, so we have star here, no star here. It's simply equal to g star of s x star of s. Nice. It's very nice, right? Okay. So then what we do is, let's move on. H of s is equal to, no, that's h of s. Okay. Decline it. Okay, that's it. Y of s is equal to h of s times u star of s. That's great. Okay. So let's sample and obtain y star of s equal to, since we have already star here, what we can do that h star of s times u star of s, it is equal to h star of s, g star of s, x star of s. Okay, so the good thing is this is star, this is star, this is star, this is star, and everything is star Laplace transform, which means that they're technically is a discrete time equivalent, and we can write that y of z is equal to h of z, g of z, x of z. Okay, and this is my combined transfer function. Let's call it t of s. Okay, so it means that I can separately discretize g and h, and I am good to go. Okay, very good. So let's solve a different one. Okay, now there is no sampling it between two transfer functions. Okay, just at the beginning and at the end. Let's try to find the result. Okay, so u of s is equal to g of s times x star of s. Okay, y of s is equal to h of s times u of s. Okay, y of s is equal to h of s. Okay, let's use u here. G of s, x star of s. Okay, I want y star of s equal to g of s, h of s, x star of s. Okay, star. So I have star here, no problem. Okay, so it means that I can star everything else. But the bad thing is, since g and h are in multiplicative form and there's no star here, I can only write this. It is equal to g h s, let's say star, x star of s, and y star of s is equal to gh star of s, x star of s. Okay, and if you find the z domain transfer function, y of z is equal to ghz x of z. Okay, so what is ghz? Okay, in order to find ghz, what I need to do is compute g of s, h of s, and let's call it, I don't know, a of s. I need to compute a of t, which is the inverse Laplace of this. Compute a k of t, take the z transform, and this is my az, which is equal to gh of z. Okay, so it means that I cannot separately discretize g and h. I can only do it by first combining them, than discretizing, and it is structurally different from what we are doing here. It's of course different because sampling should change the system behavior. Okay, it may be big, it may be small, but it certainly changes the behavior of the system. I think it's obvious that. Okay, so and now, okay, let's look even more important cases, feedback diagrams, which is quite important for our course. Okay, so let's analyze the feedback structure. We have R of S or R of T. Okay, so reference signal is continuous. Okay, we have Y of S or Y of T. It's continuous, of course. Okay, so when we sample here, okay, we obtain Y star of S, but as you can see, this sampling is somewhat separate from the feedback block. It can happen, it may not happen. It changes from system to system. Okay, Y of S is multiplied with an H of S continuous time transfer function, and we subtract R of S or Y of S times H of S. Let's say this is F of S to obtain E of S. We have an error signal between our measurement and our filtered output. Okay, so this is generally a filter, and it can be a continuous time filter. Okay, after computing the error in an analog domain, we discretize the error signal, which is quite like common in digital control system. Instead of just discretizing the output, we take the difference between the reference and output and discretize it. Okay, and this error signal E star of S, which is technically a discrete time signal, but we treat it as a continuous impulse train like signal, is filtered by a transfer function which looks like a continuous, but we know that it can have both continuous and zero threshold like transfer functions to obtain Y of S. And the goal is, can we find Y of Z divided by R of Z? Okay, so the basic idea here is, as you can see, we don't directly sample R of S. So in order to compute that, at some point we should have sampling like this, R star of S. Okay, it's kind of a fictitious sample. Okay, very good. So let's clean it and let's try to find it. Okay, so let's start from E of S. So E of S is equal to R of S minus. Okay, so one of the most important mistakes, I don't see mistake, but it's kind of a bottleneck. I generally try to avoid using Y of S in my derivations. Okay, so I will try to find the transfer function from R to E star. Then I will try to find the transfer function from R to Y. Okay, I find it much easier and it's generally gives a clear space for you. Okay, so it is equal to what? E star of S, okay, G of S, H of S. Okay, that's good. There's no problem with that. Okay, this is my expression. What I can do is I can take the star of both sides. Star. This gives me that E star of S is equal to R star of S. As you can see, I directly obtain R star of S, which is equal to E star of S. So what I need to do is, I cannot separate G and H from each other. It is equal to GH star of S. Okay. So when computing feedback transfer functions, it is generally okay to combine transfer functions because since I know G and H, it's no big deal. Okay, I can easily compute that. It's just a computational step. But if you involve Y, you can stuck because you don't know Y because you don't know either input yet. Okay, so what I can do that E star of S 1 plus GH star of S is equal to R star of S. Okay, that's great. So what I computed is E star of S divided by R star of S is equal to 1 over 1 plus GH star of S. Okay, that's great. So what I need to find is Y. I know that Y of S is equal to E star of S times G of S. If I sample this, Y star of S is equal to E star of S times G star of S. I know this, and if I use it, y star of s divided by r star of s is equal to g star of s divided by 1 plus gh star of s. Okay, that's great. And let's clean everything, or some of the stuff, and write the z-domain transfer function here. Okay, y of z divided by r of z is equal to g of z 1 plus gh divided by z. So what does it mean? It means that in order to compute the transfer function between y and r, you need to separately take a discretize g of s, which means that you need to compute g of t, g of k, and g of c. It's for the numerator. But for the denominator, you need to combine g and h, which is a transfer function such as like a of s, take the inverse Laplace, compute a of t, sample it a of k, and compute a of c, which is equal to gh of c. It's kind of indirect, or it may not be very intuitive at the beginning of the course, but you will get used to this kind of differences from what we learned from feedback systems and signal systems courses. Okay, that's great. So now let's solve a simpler one. Okay, yes. Now this is more typical. Okay, so we have output. It's not that typical, but but it's a little bit more typical. So y of t, but we sample it and obtain y star of s here. Okay, so now y star of s is technically a discrete time signal, but we treat it as a start continuous time signal. We have h of s, we have r of s. It still seems to be a continuous time signal. Okay, we have an error signal. We sample it, a star of s, g of s, and y of s. And let's do the same thing and try to find a transfer function between y of z and r of z. Okay, so let's do that. So I will do the same thing. A star of s is equal to r of s, okay, minus, okay, what I need to do is, now I can use y star of s because there is a sample here, y star of s times h of s, okay. So I want to take the star of both sides. E star of s is equal to r star of s minus y star of s h star of s. So everything is star, there's no problem. Now what is y of s is equal to e star of s times g of s. Okay, that's good. So it means that I can take the star. Y star of s is equal to e star of s times g star of s. Okay, this is y star of s. What is e? Y divided by g star of s. Okay, so y star of s divided by g star of s is equal to r star of s minus y star of s h star of s. That's good. So y star of s is equal to g star of s r star of s minus y star of s g star of s h star of s. Now everything is very clear. Y star of s divided by r star of s is equal to g star of s divided by 1 plus, okay, g star of s h star of s. That's great. We found the transfer function, and if we discretize it, we will obtain it y of c divided by r of c, which is equal to g of c 1 plus g of c h of c. So different from the previous system, where you cannot separate g and h for the denominator, because we have a sampling inside the loop, extra sampling inside the loop, we can now separate g and h when computing the transfer function. Okay, so that's all I want to talk about today, and all the concept of pulse transfer function. In the next video lecture, we will directly talk about how we can discretize real systems, such as we have a plant is a transfer function, we have a zero-order halt, we have a sampling, we have a discrete time controller, and what is the structure, how we can describe a real transfer function or digital control system.